is the last element. So the way I do this is I set tail one behind or negative because when we enqueue, right, when we add into the queue, the way I do this, I check is it full, which is you can see above, is making sure the count, which is just how many packets are there, and we initialize that to 0. Is that equal to the max size? So if it's not full, if we can add more, that means we're not going to override memory that isn't currently representing something important, right? So there's memory there of a packet that used to be in the queue, but then since we've dequeued it, and so effectively to us, it doesn't matter. And so this is another example of modifying state because the value did mean something, and now we're gonna change that value, we're gonna override it. Um, and a lot of programming paradigms that we've talked about, like functional and object-oriented, they know with encapsulation versus kind of in functional, like everything's immutable. Here, obviously, there's immutable types, but you can rewrite over the memory and kind of make it your own. And it's a lot more about what you do than how you do it. I feel like is a good way to say it. Again, sorry, if a little scatterbrained, but the point I'm trying to get at is a good example of managing the memory and kind of making it our own, right? So, like if we had written 1024 packets, but then since then we've dequeued like 50 of them, we can safely override the zeroth index one now. So that's what the module is doing. It sets the tail to that. Um, yeah, it increments the count, adds the packet to the list of packets, and then dequeuing kind of does the reverse. Tells us what packet we're looking at, and then moves the head forward because we've dequeued where the head was at before, and then decrement the count. So again, this is an example of using the memory and then like obviously stepping through um the code, right? Is nothing's recursive or no encapsulation. It's kind of line by line. And then there's also these subprograms, right? Like is Q full? We use is Q full, we reference that here. So a lot of subcram so oh my God. Subprograms being used. So again, this is why an imperative language like C is so powerful because it can interface really well with these low-level concepts and allow you to do powerful things, even though it's not object-oriented, right? You can make a data structure like a queue. Obviously, you can't really effectively make more complicated relations like an object-oriented, but you can still make something like a queue. And then let's just get to the meat and potatoes of it all, the main function here. So, and again, this is also a lot of documentation. I don't know if I can explain this super well, but I'm doing multi-threading for this. So I create two threads. It's up. I don't know why I went down. The zoom overlay is in my way. But we create the packet queue and then we create a mutex so we can lock the threads so they don't write over each other. Because basically what multi-threading allows us to do is to run this read thread function and this write thread function um, together at the same time, right? With different threads. And so we're able to kind of create a an infinite loop, right? This concurrent model will just while one and then it keeps running this. But then both of these functions have to access the queue. And I feel like I need to explain why. So what read thread is doing is it's reading. So ton is creating this connection with the kernel, right? With the Mac OS kernel. It's that API connection. And so what it's doing, as you can see here, is we're reading the packets from the kernel from that connection. So it's getting all the packets that's sent to a certain address that the kernel knows, right? And so we can read all those packets through that ton connection. And so then this read thread, it's getting all those connections. And then when it gets something, right, it has to lock the queue so that it can enqueue something. Because imagine if both these threads tried to access the same thing of memory at the same time, right? It would mess up logically what you were trying to do. It would be like a race condition, is what they call it. So to prevent that, you lock the the thread, or I don't know the right verbiage for that, but you're making it so the other thread can't access, or no other threads can access the memory at that time. And so then we can safely enqueue and we can access again the memory. It's a lot about state imperatives, a lot about state. So it's accessing that memory in that list we were talking about for the that represents the queue, and then it unlocks it. And then what the write thread can do is if the queue is not empty, it starts dequeuing them. Right. So the queue then effectively makes it so the read and write can work at their own pace, so they're not bottlenecked by each other. And so when the write thread has something to dequeue, that means like, oh, we have a packet ready waiting for you. And so it can lock, right, lock using the mutex, it locks it again, so the other thread can't access the same block of memory. So there's no race condition, we don't mess up any of the logic there. And then we dequeue that packet, and then that's when, okay, like the write thread would then do the logic, like it would send it to the server, and then the server, and then we would encrypt it here and whatnot, like what a VPN does. This would be the logic of like what makes a VPN a VPN. But just for this demo, I just print out the packet length just to show that it's working. And I didn't really have time. It's been a busy last week, as you can tell. I'm doing this right at the buzzer. And again, sorry, this is a little scatterbrained. Um, but again, like these threads and like mutexes and whatnot, it's also managing state, and it's a lot of, procedural abstraction, another one of the big five about imperative, right? And how like it has these functions, and you can abstract them too with like the includes, like the header files. So like we don't even have to see the code. Well, we see the code for write thread. We don't even have to see the code for open ton, right? We don't even need to know what that is to edit this main.c. You don't even need to know what this does. It abstracts it. And then obviously it abstracts read and write here. Like, I can just make the threads do them. It doesn't really matter what they do. So obviously I know what they do 'cause it's in the file, but it's abstracted in a way that I can work with them without even needing to know what they do. And that's made more apparent here when it's in an external file because, I mean, open ton was like 50 some lines of code, and it's like I don't even need to know anything that's doing. I just know it gives me an int FD, and I use that however it needs to be in the context. So that's how the abstraction works. The loops, because obviously in functional there's recursive, right? They don't have loops. And OOP, it's more about the encapsulation and about the relations between objects. So here's a lot more like, I don't want to say logic because that kind of sounds like declarative, but it's a lot more like statements, right? Like how you do something. So we have this while loop forever, and this allows that concurrent connection that the write and read threads are always going, always looking for packets and always checking the queue. So that's only possible with the loops. Again, a lot of conditionals to cover that again, like checking is the queue empty, because we wouldn't want to dequeue if the queue wasn't empty. I think I might have double coded it 'cause I think in the DQ there's a conditional too to make sure. So this might be a little redundant, but the point still stands that, the conditional, that it's all like very linear logic and imperative. It's very like how you're doing it, right? How am I re achieving that result? And it's very idiomatic this way. It's very easy to read imperatively. It's very, okay, like if this is true, this. And so that's how conditionals help that instead of having to do something like recursively or whatnot. And yeah, I think I've covered everything. Memory, variables, right? How the context of memory can change based on how we're using it. Talked about like with the cues and with typecasting. So I hope this has been coherent enough. I hope it's clear that this is a very imperative program. I don't know why I saved that. I hope I didn't do something bad there. And then to run it, finally we'll get the demo. And so as you can see, it's waiting here because it prints all internet or all packets sent to this connection. I hope, and that's what this other tab is for. I can't see because my like webcam for Zoom's in the way. Oh, okay, I'm sorry, but let's see if we can figure this out. This was also a lot of just looking it up. Um, okay, that worked. So let me do that. There we go. Okay. Sorry about that. Um, so again, for the Uton, because Mac uses it, I couldn't tell you what Mac uses it for, but it's, I mean, it's the way Mac processes like IP protocol stuff. So we'll stop that. So it's Uton 8 because there's 8 other processes, 0 through 7, and I just set it in my code to the next available one. You can actually see that if I do. Again, I'm sorry if this is going on forever. Uh, right here. So this, again, this is kind of trivial and it's how it's coded in the API here, but um, setting this SC unit to 0 just tells it to look for the next available connection. So it chooses 8. So I sort of that connection under the name 10.0.0.2, and then I'm pinging that. And then as you can see on the left, we're getting that packet lengths. I guess it pings, a ping is 88 packets in size. I don't know if you can change packet size through ping um, to test that. But yeah, it is clearly working. It's detecting these packets. I didn't print like which thread was doing what because that was more mutex work, right? For blocking IO. I didn't want it to both write to the same memory for outputting it to the console, so I didn't bother doing that. I'm sorry if that would have been cool to see, but as you can see, it is outputting, so it's getting the packets from Uton, that connection from the kernel, and then it's putting it in that queue, and then the other thread is reading from that queue, and when there's something to output, it dequeues it, and then it prints it out here. And as you're seeing, the packets we're sending to this address are coming up over here. And that's what I made in C imperative. I hope this was somewhat cohesive and made sense. I'm sorry if I've said that also like 5 times. It's been a long week end of the semester, but thank you for a great semester. I learned a lot in this class. I actually really love this class, especially the functional at the end of Haskell. I thought like, oh, who's gonna need to know this? And I actually really enjoyed learning about it, and I thought it was really cool. So thank you for the great course. Hope this was a cool project. And yeah, adios.